Okay, so we'll mention one more class of functions, and then we'll get on to a technique. So let's read this carefully. The quotient f of x is equal to p of x over q of x of two polynomials, p and q, is called a rational function. That's how we can fill this in. So functions of this form, that's what they're called, right? So when you see the word quotient, that's just referring to the fact that you've got something as a numerator and something as a denominator, right? That's what the word quotient means in this context. So if you put two polynomials together using a fraction, the result is a rational function. So let's just look at an example of one function that is a rational function and one that's not. So if I say f of x is equal to 13 x to the 5 minus 10 x to the 4 plus 11, I'm kind of more or less making these up as random as far as the coefficients go, over 2x minus 1. It doesn't really matter too much what the coefficients are, because look, we've got, what's the numerator? 13x to the 5 minus 10x to the 4 plus 11. That's a polynomial. What's the denominator? 2x minus 1. That's a polynomial as well. In fact, it's a linear function, but that's certainly still a polynomial. So you've got a polynomial divided by another polynomial. That means this function is rational. But let's look at a function that's not. So I'll finish this sentence by saying, but g of x, I'll write this as x cubed plus x plus 1 divided by x squared plus the square root of x plus 1. Okay, so is that rational? Well, the numerator, x cubed plus x plus 1, the numerator is a polynomial. That part's good. What about the denominator? Well, we've got x squared plus the square root of something, x plus 1. Is this a polynomial? And the answer is no. We've got a square root that has x plus 1 underneath it. And we can't, we're only, for polynomials, you're only allowed to have several terms, well, any finite number of terms, each of which has to be a multiple of a power of x, a whole number power of x, right? And this does not fall into that category, right? The square root of x plus 1, that's not allowed in the definition of a polynomial. So the denominator is not a polynomial, so therefore this entire function is not rational. So let's say is not. There, we've got two examples in one sentence. This function is rational, but this function is not. Okay, so sometimes you might be in a situation where you've got some radical symbols like a square root, or I won't get into any examples with a cube root or a fourth root, but in general it could be any root at all. And you might want to try to get rid of the radical symbols in the denominator at whatever cost is necessary. But as far as what the cost will be or how you will do that, that's going to come after. But for now, let's just finish this sentence. If you want to rewrite a fraction in order to remove any radicals from the denominator, so in other words, get rid of, like, say, square roots or any kind of root symbols, that's called rationalizing the denominator. So let's put that here, rationalizing the denominator. Okay, so you're not making it a rational function, but you are rationalizing part of it in some sense. So let's look at an example, and I'll show you what I mean. So let's follow the instructions here. Rationalize the denominator of each expression. So for part A, we've got 1 over the square root of x plus 1. So we've got a radical symbol in the denominator, and we would like to remove it. But you can't, I mean, I could just write 1 over x plus 1 and just not write the radical symbol. That might be one way of getting rid of it, but that's not what we mean here when we say rationalize in the denominator. We want to actually rewrite this fraction so that it's the same fraction, just expressed differently. So the only thing you can really do is, well, you can multiply by 1, because that's not going to change anything, or you could add 0, and that's not going to change anything either. And this is going to be one of the cases where we want to multiply by 1, but just in a very specific way. So I'm going to start by just writing the next step here, or part of the next step. Right, if you look at what I've written so far, nobody can call me a liar, because I've just written 1 over the square root of x plus 1 is equal to 1 over the square root of x plus 1. Well, I've just written the same thing on both sides of the equation, so of course they're equal. But I'm going to add something to the right-hand side, or not literally add it, I'm going to multiply it. But this is what it's going to be. I'm going to multiply it by the square root of x plus 1 divided by the square root of x plus 1. Right, so look what's happening. If I were to cover up everything here, and you just have the square root of x plus 1 over the square root of x plus 1, that's a fraction where the numerator and denominator are the same. So this entire fraction is equal to 1. So when I put this multiplication in here, the equation is still true because I'm just saying that 1 over the square root of x plus 1 is equal to 1 over the square root of x plus 1 multiplied by 1. And of course that's true. So I haven't changed it as long as I multiply by 1. Okay, well what effect is that going to have? Well, how do I multiply fractions? I just multiply the two numerators. So 1 times the square root of x plus 1 is going to give me just the square root of x plus 1. Now what about the denominator? To get the denominator, I just multiply these two denominators. So I'll just have the square root of x plus 1 times the square root of x plus 1. So actually, what this is going to be is this is just going to turn into the square root of x plus 1 divided by x plus 1. So why did that work? Well, let me just add a comment in here. I won't normally show these details, but really what's happening, if you have the square root of x plus 1 times the square root of x plus 1, that's really, anything times itself you can just write as a power of 2. So this is really just x plus 1 in a square root, but then all squared after. And if I square a square root, the square and the square root cancel, and I just get x plus 1. So that's why when you multiply these two square roots, you really just get x plus 1. Okay, so that's I wouldn't normally write that, but that's a reminder. Okay, so normally we'll just gloss right over that step. But look what happened here. We've got a chain of equalities here between what we started with and now a new fraction that does not have a radical symbol in the denominator. And that's what we mean by rationalizing the denominator. It looks like the price we paid is we introduced now a radical symbol in the numerator. So it's not perfect, right? We still have a square root symbol, but at least now it's not in the denominator. So as for why you would want to do that, well, it's going to depend on the context, but this is an important technique. Okay, so for the second one now, the second example, 1 over x plus root 2, there's a similar trick we can use to solve this one, or to rationalize the denominator here. We want to get rid of that square root symbol on the denominator, right? It's on a 2, but there's still a square root in the denominator. And for this example, we're going to need to remind ourselves about a certain trick. So I'm going to write a note up here, a reminder. So remember, if I have two numbers, which I'll use capital A and capital B to represent them, I can rewrite something of this form. A squared minus B squared, I can rewrite it as the product where the two factors are A minus B and A plus B. That's a special factoring formula, and it's referred to as the difference of squares formula. I'll just write difference of squares, but some people call it the difference of squares factoring formula or the difference of squares formula, whatever you want. But it's really just, if you hear difference of squares, someone's referring to this formula. So we're going to actually use it in reverse. So I'm going to start off the same way. I'm going to try to multiply by 1, but do it in a clever way. So I'm going to start with just, of course this is true, right? I've written the same thing on both sides of the equation, but I'm going to multiply the fraction on the right-hand side by x minus the square root of 2 divided by x minus the square root of 2. Okay, so, and I'm going to actually just put some brackets here to make this a little bit easier to read. This is a personal choice. You don't have to do it, but I certainly find it makes it a lot easier to read if you do that. It just reminds you that you're multiplying fractions. So if we multiply the fractions, what are we going to get? Well, our denominator is just going to be the product of x plus root 2 and x minus root 2. So we can write that down. This will be our denominator. And the numerator will just be x minus root 2. Okay, now what's going to happen in the denominator? Well, if I want to draw your attention down here for a moment. If I have x plus root 2 times x minus root 2, that's what the denominator is. Well, let's apply the special factoring formula up here, the difference of squares. Think of this as the right-hand side of this equation where a is equal to x and b is equal to the square root of 2. Okay, I've got them in the other order. The addition one happens on the left, but it doesn't matter. I've got something plus something, and then the same, I got something minus something, right? And the x's match up and the root 2's match up, so you really have this expression. So I can write this as x squared minus the square root of 2 squared, right? Which ends up being x squared minus 2. So that's why this works, because now if I go back up to the original context, I've got, well, the numerator is going to be x minus root 2, and the denominator is going to be x squared minus 2 because of this mathematics here, right? If you multiply these two factors, it expands into, or pardon me, not expands, it turns into x squared minus 2. So you get x squared minus 2 in the denominator. So again, we've done it, right? We've rationalized the denominator. The denominator of this fraction does not have any radical signs in it. Again, just like before though, we've introduced a radical sign in the numerator. So we haven't gotten rid of all the radicals, but at least we got rid of the one in the denominator. Okay, that also works for the third one, part C, the exact same trick. By the way, let's clean this up. I'll just put reason here. So just to remind yourself, this is just the details of how this step turned into this step. And I want to actually add one more comment before we do C. This is referred to as multiplying by the conjugate. Okay, this technique that we just did, it's called multiplying by the conjugate. Okay, so what does the word conjugate mean? Well, when we had x plus the square root of 2, x minus the square root of 2, this is the conjugate of this. So you're multiplying by the conjugate on both the denominator and the numerator. That's really what you're doing. That's why we call it that. And for part C, the same idea works, right? We've got 1 over root x minus y. And if we want to get rid of the radicals in the denominator, we're just going to multiply by 1 in a clever way. We're going to multiply this by the square root of x plus the square root of y divided by the square root of x plus the square root of y. Notice we just say, okay, there's a subtraction here, just flip the sign and make it a plus, because we're still going to want to take advantage of this rule. Okay, so what's going to happen? Let me just put some brackets here, just good habits. So what happens? You end up getting the square root of x plus the square root of y. If you multiply the denominators, apply this special factoring formula, you're going to end up getting the square root of x squared minus the square root of y squared. And what's that going to turn into? It's just going to turn into x minus y. So you get root x plus root y all over x minus y. So again, we got rid of the radicals from the denominator, but at the cost of introducing them in the numerator. But all three of these examples are examples of rationalizing the denominator.